Recording in progress.
Okay guys, we talked about a number of things. In deadlock. So what I need to know is, when does a deadlock happen? When does a deadlock actually take place in a system?
When you have two programs trying to do the same memory.
Okay, any other answer? Okay, shall I? Yeah?
When the four conditions take place?
When four conditions in a system take place, all of them, all the four. Name one of those conditions. Yeah? Yeah?
Mutual exclusion.
Mutual exclusion. What's mutual exclusion? You know what mutual exclusion is?
You have diffused resources away from the process that is.
No, that's non-preemptive. What's meant by mutual exclusion or mutual exclusive resource? Yeah? A resource can only be used by one user at a time. Only one user at a time. What's the second condition? I need another condition. So one of them is mutual exclusion. Any other conditions? Yeah? Non-preemptive? Is that why I said? Yeah? Anything else? Hold and wait. If a process that has a resource and needs a second one, if the second one is not available, if that process is allowed to go in a waiting state while holding the first resource, then that's what we mean by hold and wait. If that's allowed in our system, then that's a condition that can contribute to deadlocks. And then finally, the circular wait. If we get processes in a circle, that one is waiting on the next, and the last one is waiting on the first one, and that's called the circular wait, and that's a deadlock. Okay. How do we prevent a deadlock? Any idea how a deadlock can be prevented? By getting rid of at least one of the conditions. If we can get rid of two, that's okay. But at least one of the conditions, and sometimes it's possible. How can we get rid of the mutual exclusion condition? Any idea? An example of that is spooling. That's turning the printer from a dedicated device to a shareable device into a virtual device. Anybody knows what a virtual device is? What's a virtual device?
Dedicated device converted to shared device, but it's not completely shared.
Thank you. A dedicated device that is turned into what seems to be a shareable device. It's not fully shareable, it's not, but we say it's virtually shareable. All right, good. How can we prevent hold and wait? How do we say we don't allow a process in our system to have a couple of resources and needs another resource? We don't allow it to go on waiting while holding those resources.
Knowing the resources needed?
Yeah, maybe forcing processes to declare all the resources they want at the start, and we don't allow them to start until we have everything for them. So they will never need another resource. They have all the resources once they start. And that stops them from, hey, we need another resource, we might have to wait for another resource. How do we stop circular wait? Any idea how to stop, prevent, or remove the circular wait condition? Anybody got these other kind of questions you'll get in a test or an exam? So if you don't know them, find out the solution, the answer to them. How do we prevent circular wait?
Set requirements.
If we get all the resources we have in one long list, in a particular order, any order, and we have a protocol, if you need any two of those resources, take the ones at the top first and then the one that's lower. So we have an order. So with two processes, they need resource 1 and resource 5. They're not allowed to go for 1 and the other one go for 5. Now everybody has to go for 1 first. So whichever one gets 1 first, then can go to 5. The other one has to wait. So we will never have a circular wait. But we can't always prevent a deadlock. We can't always remove those 4 conditions from our system. A lot of the times that's an impossible task. So we go into deadlock avoidance. That means we avoid a deadlock. And to avoid a deadlock, there's an algorithm that's used, and it's called Banker's algorithm. And Banker's algorithm asks processes for the maximum resource they have, and they start allocating them and keep a track of how many does this process need and how many have we given it, and what does it still require. And if a process asks for a resource, we don't give it immediately. We say, what if we give it? What happens if we give this resource? Is our system going to turn into an unsafe state, or it will continue to be safe? If it continues to be safe, we'll approve it and we give the request, satisfy the request. But if our system goes into unsafe, then we say no, we will not, we let it wait, let that process wait. If we give that resource to this process now, we will be in an unsafe condition. And the next thing, is, what is a safe system? When do we say this system, our system is now in a safe state? Anybody knows the answer to that? Okay, the system in a safe state, if let's say there are 10 processes and they all need some resource, number of resources, they have some and they're waiting on others. And we still have a couple of resources or some resources left unused. If we can satisfy all the processes with what we have, then the system is safe. So that's how you know if the system is safe. If you have a number of processes competing and we have few remaining resources, if we can satisfy all the resources, all the processes with the resources we have. So for example, some process needs 2 resources, some needs 7, some needs 4, 3, and we have about 3 resources. Can we satisfy them? We satisfy one at a time. Of course, if they all they need about 50 resources altogether, but we just take it one at a time. This process needs 3, and we have 3. Let's give it to this process. And this process then will finish and give us back all the resources it has, and then we look at another one. If we can do that one at a time, but satisfy everybody, then okay, the system is safe. If the resources we have, maybe you need to go and discuss it outside, I'll come back here. Please. If we cannot satisfy the request of all the resources, then, or all the processes, the need for all the processes, then that system is not in a safe state, and therefore we say no, we will not allocate that. We'll have a couple of examples just to work that out, and how you need to work it out. In order to work it out, you need to kind of create a table or a matrix of what's the total number of resources, or what resources are still available. So, first, what you need is the maximum resources each process has. Let's say we have process 1, process 2, process 3, process 4. A number of processes that are competing for a resource, or number of resources. But you need a column for each resource. We'll just look at one resource. We see what's the maximum that each process needs. Let's say this one still needs, altogether, it needs 7 sets of this resource. This one needs 4, this one needs 6, and this one needs 2. And then you need to see what is already allocated to each process. Maybe this process needs 7 files. It's already been given 2 of those files. This one needs 4 files. It's only got, say, 1. This one got 0 files, and this one, I don't know, got 2 as well. So then you need to find out what's the remaining needs of each process. What do they need? Say this process needs 7. We've already given it 2. So it still needs 5. This one still needs 3, right? 6 minus 2. This one still needs 4, and this one still needs 2. If our system, right now, you can find out what's the total allocated resources. We've already given 2 and 1 and 2, that's a total of 5. This is the total allocated, in this case 5. We've given 5. And our system altogether has 7. That's the total number of resources is 7. We only have 7. We've already given 5 out. We're almost out of resources. Is this system in a safe state or not? To find out if it's in a safe state, let's see if we can satisfy every process in the system. All of them. Can we satisfy them all? How much do we have? What's the remaining? Well, what's the available now? What's available in the system? Altogether 7. We've already allocated 5. There's only 2 left. That's what we have in the system. 2. So, let's see. You need to go through this and find what we call the safe sequence. First, we need to decide, is this system in a safe state? That's if we can give everybody, all these 4 resources will finish. Can we finish them all? If we can, that's the system is in a safe state. And we also need, what's the safe sequence? I mean, which ones can we allocate in which order shall we make the allocation? Well, that's simple. You start, okay, we have 2, and this is what each process still needs. Remember, as we explained yesterday or last time, is that a process needs like a bank, somebody taking a loan from a project. This is why this is called the banker's algorithm. If somebody wants, say, 10,000 euros to get into a business, or maybe 100,000 euros to set up whatever it is, let's say a shop or a hairdressing salon or whatever it is, so they need to get the stuff, the equipment, the shop, the decoration, the staff training, and then they start making money. So if they ask for 100,000 euros, we give it to them. Sometimes they say, okay, we got a shop, we need 10,000 out of that 100, whatever. This is like the maximum they need, and so far they got this much. When they get the loan, then they get it on installments. All right, you want some money now to get training, to buy equipment, here it is, but that's the maximum. Once they reach the maximum, then they're finished, they'll start running with the business, and then they pay us back. They can only pay you when they take the entire loan. So this process will not start paying you that needs 7, it's got 2 now, still needs 5. It's not going to return those 2 or anything until it gets 7. And then it says, okay, now I'm finished, there you are. So a computer program that needs 3 files and a printer, it will not return those 3 files and printer until it reads everything from all those 3 files, so it needs the 3 files and the printer, and once it's finished, it'll give you everything back. That's the way things work. So you need to go through those processes in order to find the safe sequence. Right, process number 1. Can we satisfy all the needs? Imagine, the way you look at it in a bank or something, imagine tomorrow, if these are customers, and for example, loans of 7,000, 4,000, 6,000, this guy, out of the 7,000, we gave them 2,000, they still need 5,000. We're going to think tomorrow they all arrive and they say, give us the rest of the loan that we asked for, that they were approved for. So imagine if this process comes and say, give me 5 now in order to finish. Can we satisfy it? No. We only have 2 left. So process 1, no, we cannot satisfy process 1. So go to process 2. Can we satisfy process 2? It needs 4 altogether. It already had 1. That means it's 2. It needs 3. We can't satisfy it with 2. So process number 2 also will not work for us. Neither process 3. So the only one we can satisfy is process
4.
Okay, 4, but that's not a very good system. That system is in a... Okay, let's say, so process 4 is okay. We can give 2 of those resources. So our available now, the new available is going to be, at the moment we have 2, but we're going to take those 2 and give it to it. So now we have no more available resources. So this one is okay. We've given it, we've allocated the 2 to this one. It needs 2. Let's give it the 2, and it no longer needs anything else. So this one will finish. And when it's finished, it will return, and the available will be, now it's 0, but when it finishes, it will give us the 2, and now we'll have 2 again. So process number 4 is gone. Now, we still have 2 resources. Can we satisfy any of these? No, we cannot. And therefore, this system is not in a safe state. Already, it's not in a safe state. So if you're given this information and you're asked, is this system in a safe state? The answer is now, no. This system is in unsafe state. Why? Because we cannot satisfy all the processes. We only satisfied 1. All right. Now I'm going to put it back and just make 1 change. Imagine if this system, let's go back to normal. Imagine if we had, instead of 7, we actually had 8 in total. We have 8 resources in our system. Will that make a difference? Imagine now, this is another question. You have 8 resources, you have 4 processes, this is their total needs, this is what they already allocated, and this is what they still have left. And now you need to work out what's the available now. Well, the total that's allocated is 5. In total we have 8, so it's usually it's what's available minus what's allocated, so we have 3 left. Is this system now in a safe state? Well, let's do the same thing. Go through these processes. Can we satisfy 1? No. Can we satisfy number 2?
Yes.
Yeah? Okay, well then, let's go for number 2. So, process number 2 is the one to start. If we take, out of those 3, we give it to that, what's available? 3 minus 3. So now we are available 0, but we give the 3 to this one. Oh. Yeah, so the allocated is 4, and this one turns into a it doesn't need anything else anymore. What will happen to a process that has everything it needs? It will finish. All right, so when it finishes, it will release those 4. No longer require them, it will give us back 4. So when it gives us back 4, at the moment we have 0 plus 4 equals 4. So now what's available now is going to be 4. Now let's continue. So process 2 is clear. That's the first process in the sequence. Now can we satisfy the next one?
Yes.
Yeah, good. So let's go for process 3. We have 4, it needs 4, let's allocate it. So it's, I'll just write here process 2 that we finished now. Let's go for process 3. The available resources are, at the moment, 4. We're going to take 4 out of them. So they will have 0 left. And we'll give the 4 to this one. So the total is going to be 6. And this one, it doesn't need anything else anymore. It has everything it needs. It needs maximum 6. It got 6. What will happen to it? It will finish and it will release those resources. So it'll give us back 6. So the available now is going to be 0 at the moment plus 6. And now we have 6 resources. And therefore this one now finished as well. So process number 3 is finished. Right, we can continue. Process, this one is wrong. This should be a 2. So process number 2 needs a total 2 altogether. It hasn't taken anything, we didn't allocate anything, so it still needs 2. Can we get it out of the way? Yeah, we can satisfy that one. So we still cannot satisfy, oh yeah, we can satisfy 1 as well. But let's just continue and then come back again. So it's either both of them is correct. So if you say now I'm going to go for process 1, that's okay. If you say I'm going to go for process 4, that's also okay. So I'm going to write 2 sequences and they're both correct. But we must start with 2, then 3. Now we can either do process 1 or process 4. Okay, let's go for process 4, but both of them are correct. So let's go for process 4. We're going to give it 2 out of what we have. We have 6 at the moment. So the available now in the system is 6 minus 2, and that's we're going to have 4 left, but we give those 2 to this one. Now it doesn't need anything else anymore, and it will finish. And when it will finish, it will give us back those 2 resources. So our available is going to increase from 4 plus 2, we're going to have 6 resources. Finally, we go to that one there, that's process number 1. So that's the last in this sequence. Process number 1, it needs 5, we have 6. Let's give the 5. So what's available in our system at the moment is 6, but we take 5. In order to give it to process 1, we only have 1 left. But we give those 5 to this process. So now it's going to have 7 from us, and it doesn't need anything else anymore. And when it has everything, then it will finish. It will release the 7 and give them back to us. And that's the available equals 6, although 1 plus 6, and that's 7, and that's really, where did we should have, now once we finish everything, we should have 8 here. Where did something went wrong?
7 plus 1. 7 plus 1.
Yeah, sorry, thank you very much. 7 plus 1. And that's 8, that's correct. Now we're back to 8 resources, and all processes are finished. Okay, so you should be able to go through something like this. You write what the sequence, eventually you come out with the sequence. That's the steps in order to reach, how you reach the sequence. Right, in an exam, if you are asked, is this system safe in this situation? Some student will write, yes. You might get 1 mark out of 10. Some student might just put out the sequence, and you get maybe 5 or 6 out of 10. If you give how you reach this, then you get the full mark. So this is a typical question. You are presented with the total number and the maximum each process needs and what we've already allocated, what it has already been allocated. You need to work the rest. So you need to create this column, the remaining requirements or needs of this process, and see what's, if you are given the total, sometimes you're not given the total, you're given what's left in the system. You might be told, hey, we have 3 in the system left. 3 left in the system, 3 resources. Or you might be given the total. Either one of them, it's related to how much you've allocated. Allocated 5, you add 3 to them and you have 8. If you're given the 8, 8 minus 5 is 3. And you start now with this available in the system and go through each process. Now if we can satisfy every process one at a time, then the system is in a safe state. Sometimes you ask, no, hold on, we have that system and somebody came up requesting a request. Shall we approve the request? First, you implement the request here and test it if it's safe or not after the request is implemented. And if it turns our system unsafe, you say, no, don't approve that request. We've already had an example. This is another example, just hopefully you have a better understanding. Any questions? So what's a safe state? What do we mean by a system is in a safe state? When is a system in a safe state?
When we have resources unused.
Satisfied.
Yeah, we can resources unused.
No, no, don't ignore it.
When we have unused resources and the process is being fulfilled.
How many processes will be fulfilled? 1?
No.
All of them. If we can satisfy every process, all the processes in a system with what we have of resources, then the system is in a safe state. If we cannot, then the system is in unsafe state. So if a process comes in with a request, if that request causes our system to go into an unsafe state, then we will not satisfy the request. And usually, sometimes you might have 2 resources, then you're going to have, 2 of those columns. What each one has, the maximum of resource A, resource B, resource C, and what's allocated of each resource, and what's remaining from each resource, and see if you can satisfy it of all the resources. But it just complicates matter. So this one is an easier way of looking at it. But this needs to be done for each resource, but for the resources together. Right. So that's if we cannot prevent a deadlock, this is the next best thing, avoid it. So deadlock can happen, but we keep avoiding it. If somebody say, give me 2 resources out of the 7 I need, we say, hold on, first fill the 2 resources out of the system, and then we look at our system, is it safe now, if we give those 2 resources? And if it's not safe, we say, no, we can't give you the 2 resources now, you have to wait. Now, sometimes we can't help it. We can't prevent it, we can't avoid it. And we end up having a deadlock. And deadlock kind of is difficult to identify which processes are now deadlocked. Because you might have 40 processes or 50 running, they're all running. And of course, when we say running, only one is actually executed with the CPU, the rest of them are all waiting. But something is being done on their behalf, maybe hard disks are being read from, and printers are clicking away, printing. And the rest of the processes are asleep, but they're not permanently asleep. When the printer finishes, this process will continue. Or when the hard disk is read, or the file is read, the process will continue. It's not permanently deadlocked. But out of those 50, there might be 3 or 4 that are deadlocked. And we need to identify which one of those. And have we done this? Identifying a deadlock through using the diagrams? All right, let's go through this briefly. So first, this shape here in a diagram refers to a process, and this shape here refers to a resource. And then either an arrow is going from the resource to the process. Everybody knows what this means? How to read this? This resource is allocated to this process. Allocated. So you need to remember this word. If the arrow, this is how to read this. You go to the tail of the arrow, say this resource is allocated to this process. You always start at the tail of the resource. But if the arrow is going from the process to the resource, you can think of this as a process or a program or a person. And if a person, you say, what do you want? And they point at something. That means I want that. And that's exactly what the person is pointing at the resource, or the process is pointing at the resource, and that means it's requesting. And that's how to read it. You say this process requests this resource. If you read it from the resource to the process, you say this resource is allocated to this process. That's how it's read. So don't start with the process here for this side here and say this process was, getting this resource. No, start with the resource is allocated to the process. And the last and final thing is sometimes you get a resource that has 2 dots in it. That means we actually have 2 devices of this resource. We call them 2 instances. 2 instances of this resource. If it's a printer, then we have 2 printers, identical printers. Not different size printers, different speed, no, exactly the same 2 printers. And you can allocate each one of them to a process. You can say this, whatever resource 3 or resource number 3, this instance of resource 3 is allocated to this process. Or that process is requesting this resource. So these are the symbols used. So if I say process number 1 is requesting resource number 1, that means is it pointing at it or from it? When this requests that, do we have the arrow pointing this way or from right to left or left to right?
The first one.
Right to left, right? No. Yeah, left to right, yeah. So where's the process now? Process number 1 is pointing at resource 1. How can you read that? When you read it, what do you say?
Requesting.
Yeah, read it full sentence. Process 1 is requesting resource 1. Okay. What about this? There's another process. Process number 2. How do you read this arrow? Thank you. Shukriya. Resource 1 is allocated to process 2. So you always start at the tail of the arrow, go to the head. If it's leaving a resource, you say allocated. If it's starting from a process, it means requesting. Always. So this one is process 1 requesting resource 1, but resource 1 is allocated to process 2. It's not available. We can't give it to process 1. All right, and so on. So maybe we have another process. Process 3 is maybe, and this is resource 2, resource 3. How would you read this? Yeah?
resource, yes, resource 3 is allowed to contain process 3.
Yeah. Resource 3 is allocated to process 3. And let's say the resource process 3 also is pointing at that one. What does that? How do you read that?
Process 3.
Yeah. Process 3 is requesting resource 1. But resource 1 is, and so on. Okay. What about this? What does this say? Start again. Process 2 is requesting resource 3. Okay. So, what else shall we have? All right, is this system, once we get all the diagrams, where you get a diagram like this and you're asked, is this system in a safe state or it is not? And if it is, what's the safe state sequence? So, if in this system, if we can get rid of all these arrows, that means the system is in a safe state. If we cannot, then follow them and see if there is a sequence in a deadlock. And the deadlock, if you start at any point, will bring you back to the same point. So let's start. Can we finish process 1? Process 1, it needs, you always look for the process that has everything it needs, or we can give it what it needs. And then that's finished, it will finish in time. So we assume we jump ahead in time and say it's finished. But in this case, can process 1 finish? It needs resource 1. Can we give it the resource 1? No, resource 1 is with process 2. That means process 1 cannot finish. So let's go to process 2. Process 2, can it finish? How many does it need? It needs 2 resources. Resource 1 and resource 3.
No.
Does it have both of them? It has resource 1, but doesn't have resource 3. Can we give it resource 3? No, we cannot. It's not free. It's with process 3. So it cannot finish. What about process 3? Same thing. It needs 2 resources. It has one of them, but needs the other that's not available with process 2. That means none of them can finish. What is the deadlock sequence? You start anywhere and see if it brings you back to the same point. Let's start with process 1. Follow the arrow. That brings you there to resource 1. And then you can go nowhere except to process 2. And then you can go nowhere except to resource 3. Resource 3 brings you to process 3. Process 3 brings you to resource 1. Well, we never go back to process 1. There's no way of going back to process 1. So process 1 is not in the deadlock. Let's take another one. Resource number 2, or process number 2. If we follow, see, we start at this point. We see if we can come back to the same point. So from process 2, we go to resource 3, follow the arrow to process 3, we go to resource 1, back to process 2, now we have a circular way. The arrows will bring us to the same point, to a point where we started from. Now we need to write it down. That's process 2. Starting here, we go to resource 3, process 3, resource 1, and process 2. And this is the deadlock sequence. So the system is not safe, it's in a deadlock, and this is the deadlock sequence. Sometimes you might have 2 separate deadlock sequences, and it's good to point the 2 of them. Okay, I'm going to make a simple change, and we look at the system again and see if we can.
So P3 is in the same way also.
P3 is in the deadlock. Because the angle you're looking at. Okay. Okay, I'm gonna change this diagram. And all I'm gonna make is this change here. And yeah. All right. Now, is this system in a safe state? This is the kind of question you get. Is the following system is in a safe state? If it is, that's okay. Give it the sequence. Which process should finish first? And if it's in a deadlock, give me the deadlock sequence. So now, let's look at this. We look at every process and see if it can finish. And if it does, we'll assume it's finished, and we'll take the resource, we give it to someone else. So, normally you first look at a process that has everything. Or else you go through all the processes. If you cannot spot it directly, you just go process 1, 2, 3. So process number 1, can process 1 finish?
No. No.
Why? Because it's requesting, process 1 needs one resource. That's resource 1. It's pointing at it. It's like this person saying, I want that resource. That's how you should read it. So process 1 is requesting resource 1. Is resource 1 busy or is it available? Is it allocated to another process? No, resource 1 is not allocated to anybody. If it was, like this, for example, like resource 3, there'd be an arrow going from the resource to the process. That's how you know it's busy, if it's allocated to someone else. But there's no arrow going out of resource 1 now. That means it's available, it's sitting. In fact, it's in big demand. Process 1 wants it, process 2 wants it, process 3 wants it. It's up to us now to say, give it to process 1 or 2 or 3. Normally, if this process, that's all it needs left, there's nothing else, give it, let it have it, and it will finish. For example, a process says, I need the screen. Give it the screen, you display the picture, and then I'm finished. Or give it a printer, maybe. It's a printer, print a line or a page, and then it will finish. It will give us back the printer. So, let's do that. Let's start with process 1. What do? We need to allocate, give resource 1 to process 1. That's what you need to write. Okay, so the system will allocate this resource to this process. It's requesting it, but what we will do is say, now you can have it. You don't have to draw each diagram. Now, what have we done here? Anybody can read this? Resource 1 is now allocated to process 1. We gave it to it. What happens? Process 1 now has all it needs, all resources it needs. It doesn't need anything else. It has everything it needs. What happens to a process that has all the resources it needs? It will finish and it will release that resource. So process number 1 will finish and will release this resource. So process 1 will finish, or is finished, whatever. And when it finishes, releases which resource? Resource 1. So process 1 will finish and will relinquish or release resource 1. So now resource 1 is free again. What are we going to do with it? There are 2 processes that need it. Which one would you give it to? You give it to the one that will finish immediately, if you give it. If we give it to process 2, will it finish? If we give this resource to process 2? No, it needs another resource. So can we give it to process 3? Yeah, if we give it to process 3, it already has the other resource that it needs. Now process 3 will have everything. So let's give it to process 3. Okay, that's why we pick it up. That's why we didn't pick number 2. Because you give it to number 2 is not finished. It's going to need something else. Let's look for a process that will finish if we can give it this one. So now we pick process number 3 is allocated there. Is allocated resource 1. That means we give this resource to this process here. So we change the arrow, and now see process 3 now has 2 things. That's all it needs. It needs 2 resources. It has both of them. So process 3 has all it needs. What are they? They are resource 1 and resource 3. So this process now has resource 1 and resource 3. It doesn't need anything else. What will happen? It will finish and will release resource 1 and 2. So process 3 will finish and will release resource 1 and resource 3. So there it is. This is the finishing. The finish, that means remove this arrow. Which means these 2 resources are now free. Resource 1 and resource 3. Who needs them? They're both needed by process 2. So now we allocate, or we say, either you say allocate resource 1 to process 1, or you say process 2 now is allocated these 2 resources, resource 1 and resource 3. That means it was requesting, it's no longer requesting, it's now this is allocated to it, and this is also allocated. So resource 1, resource 3 are now allocated to process number 2. What will happen to process 2? It will finish and release resource 1 and resource 3. There it is. Process number 2 finished. Now, all links are done. All processes are finished. So this is the last statement here. All processes are finished, and therefore there is no deadlock. That's how we know the system is in a safe state. There's no deadlock. And we have the sequence. The sequence, we finish P1 first, followed by P3, followed by P2. It doesn't work. It's not P1 then followed by P2. We have to finish P1 first, then P3, then P2. So you need to give this correct sequence. Any questions?